So here I am defining S cross T cross U to be the set of all ordered triples such that S comes from S, T comes from T, and U comes from U. Now define a function. Since we have already used f, so let us denote this by g, from S cross T cross U to S cross T cross U by this formula. Okay, so this is my candidate for the one-to-one correspondence. Now you have to show, just like what we have done here, that this is a one-to-one onto mapping. Show that G is a one-to-one correspondence. I am leaving this part to you. Now I am assuming that you have shown this. Okay, we now have the fact that this mapping is a one-to-one correspondence. Now how can we use this G and that F to create a one-to-one correspondence between this set and the other set? Okay, now here we are going to write it. Now since f from S cross T cross U to S cross T cross U and G from S cross T cross U to S cross T cross U are both one-to-one correspondences. It follows from should I write theorem? Yes, I can. Oh no, I cannot write theorem. Okay, wait. Correspondence. It follows from lemma 1 to 2 and lemma 1 to 3 that F inverse composition G. So F inverse, F takes me from this set to this set. So F inverse will take me from this set to this set, and then G will take me from this set to this set. So that means F inverse composition G takes me from S cross T cross U to this set. That this is a one-to-one correspondence. and this completes the solution, because that's what we wanted. We also wanted to show that between this set and this set there is a one-to-one correspondence. By the way, what have we done here? Recall lemma 1 to 2. It says that if you have two functions sigma and tau and you form their composition, which can be formed, say, then if both sigma and tau are 1 to 1, then the composition is 1 to 1. Also, if both sigma and tau are onto, then the composition is onto. Combining these two, you get the fact that if sigma and tau are both one-to-one correspondences, then their composition is also a one-to-one correspondence. That's what we have used here, but not just that. We have used also lemma 1 to 3, which says that if we have a one-to-one correspondence, then there is an inverse function of that correspondence. You remember, if sigma from S to T is a one-to-one onto mapping, then there exists a function mu from T to S such that sigma composition mu is the identity map on S and mu composition sigma is the identity map on T. That was the statement of lemma 1 to 3, and that mu, it turned out, is nothing but the inverse of sigma. That's what we have used here. You see, first of all, F is a one-to-one onto mapping. So according to lemma 1 to 3, F inverse is also a F inverse exists and is also a one-to-one and onto mapping. Have we actually proved that the inverse is also a one-to-one onto mapping? I am not sure, but it can be shown very easily. If you look at a one-to-one onto mapping, you will see that its inverse is also a one-to-one and onto mapping. So this is a one-to-one correspondence, so its inverse is a one-to-one correspondence, and then G is a one-to-one correspondence. So using lemma 1 to 2 with F inverse in place of sigma and G in place of tau, we are concluding that this is a one-to-one correspondence. Okay, so these are extra things. So this completes the solution to the third one, and now we come to the fourth one. Again, I am saying that to some people, to some viewers, all these things may be trivial, but to some it may be non-trivial, because they are new to these things. They are seeing these things for the first time, so they have not had enough time to get themselves familiarized with this enough that they become natural. So they need to go through all the details. So it's primarily for them. So now we come to the fourth one. So the fourth one immediately has two parts. If there is a so the fact that BR, okay, let me just first state this. If there is a one-to-one correspondence between S and T, prove that there is a one-to-one correspondence between T and S. Yes. Look at this one. It is given that there is a one-to-one onto function from S to T. We have to prove that there is one such function from T to S, and naturally it is going to be the inverse of that function. So here we will actually, this one tells us that if f is bijective, or if f is one-to-one and onto, then its inverse is also as a function one-to-one and onto. So the justification, I mean, although we are saying that we have completed the solution here, but its full justification needs the second exercise, I mean the following exercise. And there is a part B also. If there is a one-to-one correspondence between S and T, and between, and also there is another one between T and U. U is also a set, a non-empty set. Prove that there is a such a function between S and U. So our first solution, I mean in the solution, the first part will automatically answer this one. Let one-to-one correspondence writing, you see, again and again he is writing one-to-one correspondence. It's easy if we type it out on computer or some other sort of typing device, but writing it is cumbersome. Bijective mapping is more convenient to write. Anyway, Herstein does not care, so let us just go through it. Let sigma from S to T be a one-to-one correspondence. Then by lemma 1, 2, 3, sigma inverse from T to S exists, such a function exists. We have to now prove that. Note that lemma 1 to 3 just simply says that sigma inverse exists. There is one such mu. Okay. But the fact that that is also a one-to-one correspondence, we have to actually prove that. And do you notice one thing? The theorem 1 to 1 that we have mentioned in the previous video, that the proof of that actually demands that we prove this. So although we said there when we presented the theorem that its proof follows from the lemmas, yes, they follow from the lemmas, but the thing is that some parts of it don't follow directly from the lemma as a just direct consequence. We have to carry it out. So let us now show that sigma inverse is actually 1 to 1 and onto. Okay. Okay, for that, what shall we do? Let us first show that sigma inverse is onto. Have we shown this or not? I'm not sure. We have not. We could not have shown this, because otherwise this exercise would not exist. No. Or we showed something similar, I think. Yeah. Anyway, so we have to prove that sigma inverse is onto. That means for every element S in S, there should be an element T in T whose sigma inverse image is S. Okay, so let S, I think I need ink. So let S belonging to S be any element Okay, what I am going to do is suspiciously similar to how we proved theorem, lemma 1, 2, 3. Okay, so let S belonging to S be any element. Then okay, not then, let, since S is an element in S, so it will have a sigma image, so let that sigma image be denoted by T. Then by the definition of sigma inverse that we have defined in the previous video, then by the definition of sigma inverse we have, previous video means that one which contained all the text parts, we have S is equal to T sigma inverse. Okay, now note that since sigma is a mapping from S to T, so S sigma, which is nothing but T, is actually an element of capital T. Since T belongs to capital T, this proves that S is the image of T under the function sigma inverse. Note that we are writing T sigma inverse. It looks like this is the inverse image of T under the function sigma that we defined in the beginning of our video in the first solution. Here, however, it is the image of T under the function sigma inverse. although it seems like we are using the same notation for two different things, but fortunately they turn out to be the same. Here if you try to interpret T sigma inverse as the inverse image of T under sigma or as the image of T under sigma inverse, you will get the same thing. Okay, so there is no problem with this. So this proves that S is the image of T under sigma inverse. Hence, sigma inverse is onto. Okay, next we have to prove that sigma inverse is 1 to 1. So we take two elements in its domain, that is T. So let T1 and T2 be two elements in T such that T1 sigma inverse is equal to T2 sigma inverse. Their sigma inverse images are equal. We have to prove that T1 is equal to T2. Now let S1 be T1 sigma inverse and S2 be T2 sigma inverse. Then S1 and S2 are elements in S such that according to the definition of inverse mapping, S1 sigma is T1 and S2 sigma is T2. Okay. Since S1 is equal to S2, because you see that's what we have here, no? S1 is nothing but this and S2 is nothing but this. So S1 is equal to S2 and sigma is a well-defined mapping. We have T1 equal to S1 sigma equal to S2 sigma is equal to T2. If sigma has to be well defined, then if you take two elements in its domain, which is nothing but S, that are equal, then their images under sigma should also be equal, but those images are nothing but T1 and T2 respectively. So now T1 and T2 are equal. So you see what we have done. We have taken two elements in the domain of sigma inverse T1 and T2 such that their sigma inverse images are equal, and we have ended up proving that the elements T1 and T2 are equal. So this tells us that the sigma inverse as a mapping is 1 to 1. Hence sigma inverse is 1 to 1, and that's what we needed. We needed to show that there is a 1 to 1 correspondence from T to S also. Thus sigma inverse is a one-to-one correspondence between T and S. Okay, now next we have to prove part B. Now in part B, it is given that there is a one-to-one onto function from S to T and one such function from T to U. Then we have to prove that there is one such function from S to U. For this we don't have to do actually anything much. From lemma 1 to 2 it will follow directly. So there is a one-to-one correspondence between S and T and one between T and U. So let sigma from S to T, which we already had, and tau from T to U be one-to-one correspondences to, so plural. Now consider their composition. Sigma composition tau, which will map S to U. By lemma, one to two, sigma composition tau is also a one-to-one correspondence. Why? Because the fact that these two are one-to-one correspondences tells us that both sigma and tau are one-to-one. So their composition is also one-to-one. Just like that, both are onto, so their composition is also onto. So that's why this is also a one-to-one correspondence, and that's what we wanted, one such function between S and U. And this completes the proof of, I mean the solution to this fourth exercise. Okay. And this also forms a part of the proof of our main theorem in this section, theorem 1-to-1. It tells us that the set A of S is closed with respect to composition. That is, do you remember, if sigma and tau are two elements in A of S, then their composition is also an element in A of S. Further, if sigma is in A of S, then sigma inverse is also in A of S. It not only exists, but it is also a one-to-one onto function from S to itself. So that is justified. These two things which are actually in that theorem, this is first part and this is the fourth part. Okay, so these two have been proved. Now we are going to prove the third part, which involves that identity map. So that is our fifth exercise. This will be rather easy if iota is the identity mapping on a non-empty set S. Prove that for any sigma belonging to A of S, sigma composition iota is equal to sigma, which is also equal to iota composition sigma. So this solution is very easy. since sigma and iota are both elements of A of S. That means what? That means both are one-to-one correspondences of S to itself. So we can apply the result of the previous exercise here, and what will be our conclusion? Particularly part B, that will tell us that this composition and this composition are also elements in A of S, because they are also one-to-one correspondences. Actually the previous exercise does not say anything about this, but the solutions say it. The solution to part B of the previous exercise. In the previous exercise we had different sets, but now we have only one set, S. By the previous exercise we have sigma composition iota and iota composition sigma belonging to A of S. By the way, why do I need to conclude this? We actually have to show that these functions are equal, right? But for that to happen, I must make sure that sigma composition iota and iota composition sigma are actually functions from S to S. For that I did this. Okay. Now we have to show that they actually map every element of S to the same element, all of them. For any S belonging to S, we have S sigma composition iota is equal to what? By the definition of composition, S sigma iota. Now note that S sigma is again an element in S. Why? Because sigma maps S onto itself, and iota is the identity map on S. So iota will not change S sigma. So this is equal to S sigma. Okay, which implies that as functions these two are equal because they have the same effect on S. Also, S of iota composition sigma is equal to S iota sigma. Now S iota is actually equal to S because S is an element of S and iota is the identity mapping on S. So it has no effect on S, it does not change S. So this is equal to S sigma, which again implies that now this function and this function, they are equal. So that just proves what we wanted. So this completes the solution. Okay. Now next we come to an exercise which is somewhat different, and it has a star. That means it is somewhat more difficult than the other exercises, and that is true. If S is any set, prove that it is impossible to find a mapping of S onto S star, where S star, if you remember, is the power set of S. It is the set of all subsets of S. So what this exercise says is that we can never find a mapping which maps S to S star and it is onto. Okay. Now, since we have defined mappings only between two non-empty sets, it is implicitly assumed, since we are talking about mappings between S and its power set, that S is non-empty. So the fact that although the author writes S is any set, but you have to understand it is any non-empty set. But here the result is also true when S is empty. But since that is only one case, so we can just leave it. So now we come to the mysterious solution of this. Okay. So the solution is, or the proof is by contradiction. We assume that there is, or we suppose that there is a function from S to S star which is onto, and we arrive at a contradiction. Suppose there exists a mapping sigma from S to S star that is